Chapter 4.2, Exponential Functions. An exponential function is a function with a variable as the exponent. For example, this is an exponential function with a base of 2. Okay? The base of an exponential function must be positive and cannot equal 1. So let's just look at the graph of this exponential function right quick. Okay, if I don't know anything about its shape, then we have our old standby. Let's plot a few basic points. So if x is -2, I would have 2 to the -2. Remember, that's 1 over 2 to the +2. Negative exponents mean reciprocals, or 1/4. Then I would have 2 to the -1, or 1 over 2 to the +1, 1/2. 2 to the 0, anything to the 0 power is 1. 2 to the 1, and 2 to the power of 2. So plotting these points, we get -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4. So we get this graph whose shape looks like this. That's the shape of my exponential function. Okay, let's look at what if our base were a proper fraction. Notice if my base was 3, this would just be steeper. I'd have 3 to the -2, so I'd have 1/9, right, 1/3. I'd still have 0, 1. Anything to the 0 power is 1. But then here I'd have 3 and 9, so I'd be at 3 and 9. If it were 4, I'd be at 4 and 16. Exact same shape, just steeper. But what if my base is a proper fraction? Remember, it can't be negative and it can't be 1. So let's see what we have then. All right, then I would have 1/2 to the -2. Remember what negative exponents mean? They mean reciprocals. So 2 squared. 1/2 to the -1 would be 2 over 1 to the +1, or just 2. Anything to the 0 power is 1. 1/2 to the 1, and then 1/2 squared. So I would get -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4, and here's what that would look like. Okay, so same shape, except it's been flipped over the axes. Oh yeah, look at this right here. 1/2 to the -2 is the same thing as 2 to the +2. Right? Remember from our translations, if I have a negative in front of my x, it's going to be a reflection. Okay, so let's think about these graphs a minute then. Notice that the graph of an exponential function of this form always contains the point 0, 1. We saw that twice. Anything to the 0 power is 1. And 1 with whatever your base is. This one has 1, 2 when I had a base of 2. This one had 1, 1/2 when I had a base 1/2. It has a horizontal asymptote at y equals 0. Notice this horizontal asymptote. It's an increasing function. If your base is bigger than 1, it increases. It's decreasing if your base is in between 0 and 1. The domain is negative infinity to infinity. Remember, the domain deals with the x's. And the range is 0 to infinity. 0 to infinity, I've got this horizontal asymptote here at 0. So if I want to graph an exponential function, here's my basic points. I need to be able to get these basic points very quickly. Let's say we want to graph f of x equals 2 to the x plus 1 minus 3. Well, I want to be able to graph my basic function 2 to the x. So here's the points I want to be able to get very quickly. And then I'm going to use translations. Anything in with the x, right, affects the x values, and it'll move in the opposite direction. So I'm going to take every one of these points, I'm going to move it left 1, and then if it's not with the x, it affects the y value. So left 1 and down 3. So I'm going to come over here and I'm going to take this point and go left 1 and down 1, 2, 3. This point is going to go left 1 and down. Let me move that one down just a little bit. That's not at my half. That's my 1/4. So left 1 and down 1, 2, 3. 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 Here it is. Left 1 and down 1, 2, 3. Okay, and I still have the same shape because I'm going to add this shape to my list of shapes, and I can use translations to help me graph this. Notice all that did was shifted my horizontal asymptote down 3. Okay, so that's graphing exponential functions. Let's look at just solving an equation of an exponential function. Okay, to solve an exponential equation, notice I just have one variable now, so I should be able to solve it. Right? It's not a function with two variables where I have to draw the graph. Our goal is to either make the basis the same or make the exponents the same. If the bases are the same, the exponents must be the same. Likewise, if the exponents are the same, the bases must be the same. So for this one, because my variable's in my exponent, it tells me, hey, I'm looking at trying to make the basis the same, and I notice, yes, I can write both of these with a base of 2 because I can change 8 to 2 cubed. Now, once I have 2 to some power equals 2 to this power, the only way that can happen is if these things are exactly the same, right? So I can pull that out and say, oh, 3 minus 2x has to equal 3, and solve a very simple linear equation. So x must be 0. And yes, if we plug that in, we get 2 cubed equals 8. Okay, I'm looking over at this one and I notice they both have a base of e. Right? But this e is in the denominator and this one's not. I need to change that so I can get these bases to be the same. And remember, negative exponents mean reciprocals. So I can change that instead of 1 over e to the positive 4 to e to the negative 4. Okay, now because of my rules for exponents, I know if I have an exponent raised to an exponent, I can multiply. So that's negative 4x minus 4. And now that I have my bases the same, the only way that can happen is if the exponents are also the same. So x minus 1 must be equal to negative 4x minus 4. And once again, I get a simple equation I can now solve. So x is negative 3/5. So just make the bases the same, and then you can pull those exponents out and set them equal, because if the bases are the same, the exponents must be the same. Technically, that's the same concept for one of these, but notice this isn't really an exponential, right? This is a radical, and we've already talked about how to solve radical equations. So yes, I could figure out how to make 16 something to the 2/5, and then my basis would be the same. Or I could just use the method that we already have. I'm going to raise this to the 5/2, right? We've already done this in the radical section. 2/5 times 5/2 is x to the 1. And so now I know that this notation means the square root of 16 to the 5th, right? The denominator is your index, numerator is your exponent. So the square root of 16 is 4 to the 5th, and then whatever that is, multiply it out. What do we have? 16 times 16. 256 times 4, 1,024. All right, let's do an extra one of those. What if we had something like, let's say, 8 to the 2x equals 4 to the 5x minus 1. Remember, we're trying to make the basis the same, not just some common factor. I can't write 8 as 4 to any power. I have to change them both to 2 to some power. Same base, not just common factors. So I can rewrite 8 as 2 cubed, and I can rewrite 4 as 2 squared. Okay, now, once again, an exponent raised to an exponent. I just multiply 3 times 2x, and the same over here. 2 times 5x minus 1 is 10x minus 2. And now the bases are the same, so the exponents must be the same. And that's a very simple equation we can then solve. So x must be 1/2. All right, exponential functions and exponential equations. Let me know if you have any questions.